Students, now we shall discuss the last topic in Unit 5, that is discontinuous functions in the real line. Discontinuity functions in real line. Discontinuous functions. We discussed about continuous functions. Now discontinuous functions on the real line R. So sometimes they use R1, both are same. So now this is the topic we are going to discuss. We discussed about continuous functions. Now we are going to see functions which are not continuous and what are the points of discontinuity. Those things we are going to discuss here. Now the first definition. The first definition under this topic. What is an F sigma set? F sigma set. That is a definition. What is the meaning of F sigma? So now we going to see restrict ourselves to the real line R or R1. So now the subset D of R1 is said to be of type F sigma if that set D can be written as some union of some closed subsets where each Fn is a closed subset of R1. So this is the first definition, that is what is a F sigma set. It is a set which can be written of this format, so union of some closed sets. All the sets, each F1, F2, F3, that countable collection are all closed in R1, not in any general metric space. So that set, if you are able to write that set D a union of closed subset of Rn, then we say that D is of F sigma type. So we are giving a definition now. The first definition. Now what happens if this F is a closed set? Now if F is closed, then it is a F sigma set. How is it F sigma set? So how is this statement true? So now what is F sigma set? It can be written as union of all closed sets. Now suppose I take a closed set. Suppose not necessarily okay. F is a closed set, and now I am going to write F like this. Like this. So I name this as F1 and this set as F2 and this set as F3, F4. So what happens? This can be written as union of Fn. Already we proved that in a given space, that is here metric space is R. The full space and empty space are always open as well as closed. So all these 5 empty sets are closed. So F1, F2, F2, F3, F4 are all empty sets and it is closed by default. So this F can be written as F union all empty sets. So this one simply I denoted by F1. So what we can see here is this F can be written of this type, where each of these sets which we union them, all are closed. If that is the case, then I can say that this is a F sigma set. So what we come to know here is, if any set closed, then automatically it is an F sigma set. You may ask in shorter question, prove that if F is closed, then it is a F sigma set. This is a simple explanation. Also, and you can make a note. This is one small result. Now the next one, what about open intervals, whether they are F sigma set or not? So the next one is, any open interval you can write it as note 1, this is note 2, something like this. Any open interval in real line interval of this type is also a F sigma set. How is it? How we say that an open interval is of this type is an F sigma set in real line? We are going to prove it. Proof means just we are going to say that it can be written of the union of all closed intervals. How is it? Now, the open interval AB is the union of countably many closed intervals. What are these closed intervals is like this: a plus 1 by n comma b minus 1 by n for n in I with 2 by n with 2 by n is less than b minus a. So what is this is, see, like this, that is, this open interval can be written as union of all intervals of this type, closed intervals. What are these closed intervals? It is like this, where n varies from 1 to all countable collection of closed intervals. So any closed interval is a closed set, and this is a closed set, and this open interval is written as the union of countable collection of closed sets. Therefore, any open interval in real line is a F sigma set. How is it this one is equal to the union of like this intervals? I'll just give a brief explanation. Since see, I'll just draw the real line. See, what is I1 you see? So I'll write it here. I1 is n equal to 1, a plus 1 comma b minus 1. So what is I2? A plus 1 by 2 comma b minus 1 by 2. Next I3 is a plus 1 by 3 comma b minus 1 by 3. You just see what happens if you plot these intervals on the real line. So what is, suppose remove this one, I put a hole here, that is A, and this is B. So A plus 1 is somewhere here, A plus 1, and B minus 1 is somewhere here. I don't know exactly what is A and B, simply we are guessing. It should be definitely less than B minus 1. there is a question that whether this b minus 1 will be less than a plus 1 or this will be greater than this. That is not possible because of this condition. I will tell you what is this. Okay, now next, this interval, this closed interval, we call it as I1. So what is I2? You see, a plus 1 by 2, it will be here, less than, this is a plus 1 by 2. Next, b minus 1 by 2, somewhere here, b minus 1 by 2 will be here, and this interval is called as I2. Similarly, a plus 1 by 3 will be here, b minus 1 by 3 will be here. That interval we call it as what? I3. So now what happens, you see, I1 is a subset of I2, I2 is a subset of I3, you can visualize. So if n tends to infinity, what happens is, these intervals, this left hand side of the lower limit of that interval when n is large comes very close to a, and the right hand, the upper limit of this any interval when I is large comes very close to b. So what happens is, when I is large, this one will come very close to a, and this point will come very close to b. That is, it will be coming like this towards a, and the right hand side part of that interval, upper limit of that interval will be coming very close to b, but it won't approach b. So what happens, if you union all these things, we will get nothing but the interval without a and b, and that is nothing but open interval ab. But all these intervals I1, I2 are closed intervals. See, a closed interval is nothing but a closed set. So that is the case. That is why we say that any open interval in R1 is a F sigma set. You can understand from this diagram. Okay. Now another definition is there. Let f be a function from R1 to R1 if j is any bounded, j is any bounded open interval, j is any bounded open interval in R1. We are going to define a new real number. We define that is called as omega of f semicolon j. Same like an open ball, we are using some other, this is a real number, this is not a set, this is a real number. We will show you what is the definition. We call this as oscillation. We call this as an oscillation of f over j as, so we are going to give definition. What is this omega of f semicolon j? It's nothing but the difference between LUB and GLB of all the function values. LUB of all f of x, but all this x should come from j. The difference between LUB and GLB of all the function values, where here f equals to, this is called as the oscillation of the function over j. Oscillation of the function over set j. Now we are going to define what is the oscillation of a function over a particular element. Then if a is a real number, we are going to define another real number, that is called as oscillation of f at a point A. It's called as oscillation of f at a point A. This is oscillation of f over a set. A to B. So we are going to define what is it. That is also a real number here. It is nothing but we take the GLB of all oscillations of F over a set J, where this GLB is taken over all bounded open intervals J that are containing A. So what you can come, this is the definition. So now you can see that this oscillation of F over J is non-negative, that is greater than or equal to 0, because always LUB is always greater than or equal to GLB. So if you take the difference between LUB and GLB, definitely it should be a non-negative quantity. So that is one small result. Similarly, here we take GLB of all non-negative terms. So this also must be what? Non-negative. So geometrically, what is the meaning of oscillation? Suppose we take one set. So we don't want to do like this because we are going to see if we are taking real line. Suppose this x and y axis. Suppose this is a function f, that is doing the mapping from set A to B, and suppose this is the interval J. Suppose this is the interval J. So now the corresponding function values you have to see here. Just I am giving some corresponding function values are here, from here to here, and suppose this is a set. Suppose what is the meaning of oscillation of this function f over the set J? So what is the definition? It says it's nothing but LUB of f of x minus GLB of f of x, where this x must belong to J, here also x must belongs to J. This is a J, and you take all the function values, it is here. In this clearly I see that this is my GLB, and this point roughly it's the least upper bound for this function in that interval J, because I have taken a increasing function so that you can understand easily. So here this LUB GLB. So what is this happens is, so oscillation of FG is nothing but this number minus this number, that is this distance actually. That is the distance between LUB and GLB. Suppose this distance. Okay, geometrically this is the meaning of this. This is nothing but LUB of f of x minus GLB of f of x, where x belongs to J, here also x belongs to J. And this quantity, where this is a real number, there is a length, it's denoted by the oscillation of f over J. Okay. Like this you can imagine, suppose you take a point A. What is the oscillation of this point? That is omega of f colon A. That is, you take like this many open many intervals J which contains this point A. For all these intervals you find this oscillation. Then you take the least of all the oscillations. That value we call it as the oscillation of the point, oscillation of f at the point A. So this is the just we can understand what is the meaning of oscillation. Okay. So if there is more oscillation, then we say the function is not continuous. That's what we are going to prove now. So we are going to now use this definition and prove some theorems related to continuity and discontinuity of a function at a point A. Okay. So what it says is the number j of omega of f colon j measures roughly the distance from the lower part to the highest part of the graph on j. It is clear that if f is continuous at a, then this, and j is a small interval containing a, then this oscillation must be small. If this oscillation is big, then the function cannot be a continuous at that point A. So we just discussed what is an oscillation of a function over a set J. J must be a bounded closed interval. So that's very important. J should be bounded open interval. Okay, should be a bounded open interval. Okay. Now we are going to discuss the theorem, the first theorem into this section. If f is a function from R1 to R1 and A is any element of real line, then the following statements hold. First one, if f is continuous, at A, then the oscillation of f at the point A must be zero. There should not be any oscillation. If f is not continuous, at A, then the oscillation of f at the point A should be definitely greater than 0. So this is how we can tell that a function is continuous or not continuous, discontinuity at the point A. You can very well find it by using the oscillation definition. Oscillation of a function must be 0 at the point A, then it is a continuous function at that point A. If there exists some oscillation that is greater than 0, then the function is then that point is the point of discontinuity of the function. Okay. Now we shall prove this theorem. Proof of 1. So the first one we are going to prove. Now, so first one is, suppose we assume now that f is continuous at A, we have to show that the oscillation of f at that point A must be 0. So suppose the function f is continuous at the point A. Yes. At A. Now we have to show that the oscillation is 0. Therefore, we are going to use the definition of continuous function. Let for any given epsilon greater than 0, given, then there exists a delta greater than 0 such that the distance between, because we are in real line, we are going to use absolute volumetry. The distance between f of x and f of a is less than epsilon by 2. Instead of epsilon, I can take epsilon by 2. Because if this is my real number, for this one, there exists a delta. Whenever x and a, the distance between x and a is less than delta. So this is by the definition of continuous function. Because for any given epsilon, there exists a delta. Now, that interval j we are going to consider is taking j as the open interval. This is the open interval we are going to consider. That is a minus delta comma a plus. Actually, this is nothing but set of all points that lies between a minus delta and a plus delta. All points in between these 2 points. This interval we are going to take it as j. That's all. Then, if we consider this as j, this interval as j, for every element in j, this condition is satisfied. We are going to rewrite this this result from continuous definition of continuous function. It is same thing. We are going to write it again. Instead of interval, we are going to put simply j. This is less than epsilon by 2 for all x element of j. Both are same. We are writing it in different way. Now we are going to take, see, this inequality is true whenever I take this x, whenever this x belongs to j. Now I am going to take 2 elements. Now for any x comma y belongs to j, we have, I am going to take 2 elements from j. So what is happening? What's the difference between f of x and f of y? This is nothing but I am going to subtract f of a and add f of a. That's all. This is nothing but, by using the triangularity, this is nothing but f of x minus f of a plus f of y minus f of a. And this quantity is less than what? Epsilon by 2, because already we proved this. And this is also y. If y belongs to j, then this condition is satisfied. That is why this is also less than epsilon by 2. Overall it is less than epsilon. That is, the difference between f of x and f of y for any 2 elements in j is always less than epsilon whenever x and y belongs to j. Whenever x and y belongs to j. Whenever x and y belongs to j. In particular, this is true for even LUB and GL. So this is true for any 2 elements x and y. The corresponding function values, the difference between the corresponding function values always less than epsilon. This is true even for LUB and GL. Any 2 elements. So this is true for LUB of f of x minus GLB of f of x. This also will be less than epsilon whenever x and y belongs to J. But this is nothing but what? For every x and y belongs to A, this is nothing but the oscillation of F, with respect to the oscillation of F over J. This is less than, because we have taken all the points x and y, everything from J. Here I have to make a change here. So the corresponding LUB and the corresponding GLB of this one, so that difference also should be less than epsilon. So this is nothing but the oscillation. You can see the definition of oscillation. Oscillation of a function f over J So this is true for any two elements of J. You can take this y as x itself. So this will become what? Oscillation of the function over J, where the elements x and y belongs to J. Since we have assumed that this J is, since J is an arbitrary open interval, so J is an open interval, you can check it. J is an arbitrary open interval that containing A, you can see. J, definitely A is somewhere here. J contains A and it's an open interval, and more important, it is an arbitrary element containing A. Therefore, what is the oscillation of F with respect to A? That is nothing but you have to take the GLB of all the oscillations of F over J, where J should contain that element A, where GLB is taken over all J containing element A. Okay. So this is nothing but this, but all these oscillations over F, oscillation of F over J, where J contains A, is always less than epsilon. Therefore, if you take the GLB of all of them, that also must be what? Less than the greatest and lower bound of all these oscillations is less than epsilon. Therefore, if you take the GLB of all the oscillations, that also must be less than epsilon. Now, since epsilon is arbitrary, we have that omega of F colon A semicolon A should be equals to 0, because this is always less than epsilon for any epsilon greater than 0. Therefore, the only possibility is that this oscillation must be equals to 0. So, hence the proof of 1. So 1 is proved. See the explanation for this. Suppose omega of AF colon A is less than epsilon for every epsilon greater than 0. This implies that omega of AF semicolon A is equal to 0. We have one proof. Suppose A and B are any two real numbers. If A is less than or equals to B plus epsilon for every epsilon greater than 0, then we can prove that A must be less than or equal to B. So in place of B you put 0, in place of A you put this omega F semicolon A. So what we proved so far, A is less than epsilon, that is B is 0. So this implies that, that is omega F semicolon A is less than epsilon for every epsilon greater than 0. This implies this should be less than or equal to 0. But always omega F semicolon A is greater than or equal to 0. Therefore, these two things implies that this oscillation of F at the point A must be equals to 0. So like this you can understand. Okay. So that's why we simply write, since epsilon is arbitrary, this should be 0, just complete it. But here we have a lot of explanations. This is how we get the equals to. This is the proof of A. Now next we are going to understand what is the proof of B. So I will prove the proof of 2. So what is the proof of 2 is, we are going to assume that so we have to prove that F is not continuous, then the oscillation at the point A must be greater than 0. So now we are going to assume, that is same way, see, this is A implies B, that is A is nothing but the function F is not continuous, then B is what? The oscillation at this point A must be greater than 0. The other way to prove this, we assume that B is false. Then we have to prove that A is also false. That is, we assume that the oscillation is less than or equal to 0. That is this one. Then we will try to prove that F is continuous. So like this we are going to approach. So we have to prove that what? The oscillation is greater than 0. Suppose we assume that oscillation is less than or equal to 0. Suppose oscillation of the function F at the point A is less than or equal to 0. Actually what we have to prove is oscillation must be greater than 0. We are assuming the contrary of this. This implies that oscillation of F must be equal to 0. Why? Since oscillation at any point or oscillation over J, everything is what? Greater than or equal to 0, because you can see that's a difference between LEB and GLB. So if you assume that it is less than or equal to 0, the only possibility is that it must be equal to 0, because less than 0 is not possible. Now we shall show that, F is continuous at, see the previous theorem, if F is continuous, then the oscillation is 0 at that point. See here, if it's continuous, then oscillation is 0. So we have not proved it, the sufficient part, that is, if this is 0, then F is continuous. So but now we are going to prove sufficient part only. So now if this happens to be 0, then we are going to prove that F is continuous. So now we are going to consider, we shall prove that F is continuous at 0. Let us consider one real number epsilon greater than 0 be given, an arbitrary point. Since the oscillation of F at the point A is usually given by GLB of all the oscillations of the function F at the point J, and this is what? Just now we proved that this is assumed to be 0. So now oscillations, all the GLB of all the oscillations over J happens to be 0, then What's the meaning of that is, then there exists a bounded open interval from this I am writing here. Then there exists a bounded open interval J that containing A, because here as per the definition, all the open intervals for which we take the GLB over this, all this J should contain one A. So that's why this is possible. That is a bounded open interval J containing A such that the oscillation of F J is equals to 0, and 0 is definitely less than epsilon. Okay, already just now we proved that it is equal to 0. So there exists an open interval bounded open interval J containing A such that this should be less than, because GLB of all the open intervals means those all omegas comes very close to the GLB, but GLB itself that value is 0. So what you can tell is all the omega values they come very close to what? The GLB, but the GLB itself is 0. So they come very close to what? GLB. So you can think that this is the limit is 0. So the difference between this is less than epsilon. So that is why we write it this omega, that the oscillation of F semicolon J is less than epsilon because of this result. Okay. So okay. So, less than epsilon. Let I give this as number 1. Let us take two elements from J. We take two elements from J. Then the function value F must be, any function value must be less than or equals to LEB of all function value, and function value Y should be greater than or equals to the GLB of all function values. So this is by the definition of LEB and GLB of a functions. So for x and y, and this is true for every x in J, this is true for every y in J. Therefore now we are going to combine both of them. So what is f of x? So f of x minus g of x. F of x is less than or equals to what? So in place of f of x, we are going to put the LUB. But this is LUB is greater than or equal to this. That's why we use this one. Similarly, f of y is greater than or equal to the corresponding GLB of all the function values. So if it is negative here, sorry, not g of x, it should be f of y. So here minus f of y will be less than or equals to minus of GLB of f of y. So that's why overall it is what? Less than or equal to y. Okay, and this as per the definition of oscillation, this is nothing but the oscillation of F over J, but this is what? Less than epsilon by 1. See, this is true for any two elements x and y in J, and in place of y you can put x, so it becomes that is equal to what? The oscillation. Therefore, what we get? Therefore, f of x difference f of y is less than epsilon for every x comma y belongs to J. Since we have taken A is element of J, since A is element of J, we can take that y is equals to A, because x and y belongs to J. That is generally both x and y belongs to J. So in place of y we are going to take A, because A is belonging to J. Since A is element of J, we take y is equals to A. Then what happens to this result is f of x minus f of A is less than epsilon for every, this becomes a constant, that is A. So we are going to take that for every x in J. And this result is true for any subinterval. This is true for any subinterval, say, which is a subset of J. You can see the definition of this J, any subinterval. Therefore, what is the final result is f of x minus f of A is less than epsilon for every x in the interval, this one. That is f of x minus f of A is less than epsilon whenever the difference between x and A is less than delta. Both are same. Both are same but different notations. So what is this tells? Because epsilon is arbitrary. So as per the definition, f is continuous at the point A. And this is a contradiction. So what is a contradiction? So what is a proof of 2? We have to prove that if f is not continuous at A, then this should be greater than 0. So we proved the converse of this. So we assumed that this is equals to 0, then we prove that f is continuous. So finally what is the result we have proved is f is continuous at A if and only if the oscillation of the function at A must be equal to 0. Okay. So to prove this B, the second one is nothing but the converse of 1. So we assumed wrongly, that is this is less than or equal to 0, then we came to know that f is continuous, which is a contradiction to this. So if this condition is not satisfied, that is it's greater than 0, then f is not continuous. So this condition, that is the oscillation of the function at the point A, is a necessary as well as sufficient condition for a function to be continuous. Why it's necessary means, if this condition is not satisfied, then f is not continuous. Why it is sufficient means, if this condition is satisfied, that is enough to show that the function is continuous at that point A. So in the examination they may ask like this: prove that f is continuous at the point A if and only if the oscillation of f at the point A is equals to 0. So you can prove this. This is a necessary part and this is a sufficient part. So sufficient part is what? We have to assume that this is equal to 0 and prove that f is continuous at A. That's what we have done. Actually number 2 is the sufficient part, the converse of that. Okay, this completes the proof.